Welcome to this third recorded video for the Part B lecture notebook of the fourth module on computational applications. So what if the set A is complicated? This is referring to the set A that we integrate over, and we were just talking about Monte Carlo integration. Well, the typical built-in random number generators available in the random sum package of NumPy or the stats subpackage of SciPy are great for generating random numbers and vectors in nice geometric sets like intervals in 1 dimension, rectangles in 2 dimensions, or rectangular boxes in 3 dimensions, and generalizations of such boxes in higher dimensions. But what if the set A we want to integrate over is not an interval or box-shaped? What if we can only describe A in terms of relationships to other points or other geometric shapes? Well, we can do something referred to as accept, reject, or sometimes just called rejection sampling. At a conceptual level, imagine that we create a type of dartboard out of a simple object, like a box, that contains the set A. The set A is the target of the dartboard. If we generate random numbers and vectors in the simple object, in other words, we throw darts at the board, and we accept those darts that are inside of A, meaning we check if a dart hits the target, then we will have generated random samples within A. So some key points here. The proportion of darts that fall in A, the target of our dartboard, times the measure of the circumscribing box, the dartboard size, gives an estimate of the measure of A, which we again denote by mu of A. And I see I have a little typo there and then I'm missing a parenthesis, so I just add that. It'll be fixed for you. We may have to throw a lot of darts to generate as many random samples in A as we like. You might end up wanting to use a while loop. Let's illustrate when A is a unit disk in the Euclidean plane that we fit into the dartboard defined by this square -1, 1 cross -1, 1. So we have this square of side length 2, and we have a unit disk inside of it. Again, a suggested activity: add a useful doc string to this random disk darts to describe the role of the various parameters. Well, there's just one, which is n, and add some doc tests. So the first thing we do is throw darts at the circumscribing square. So I generate uniform random numbers from -1 to 1 of size n by 2. So the first column will be the x-coordinate and the second column will be the y-coordinate. We check which darts hit the target, which is a disk called A. So I create 2 lists for the indices of the darts that land in A and the indices that are not in A. So the first thing I do is I check the square root of the x-coordinate and the y-coordinate, the distance of those points from the origin, 0, 0. So I take x minus 0 and y minus 0, square, add up, and take the square root. That's the straight line Euclidean distance. And I check if that's less than 1. If it is, that dart fell in the disk. The index is in A, and I append to that list the index I. And then if it's not, that dart is not in A, so the index is not in A. And I append that list with I. The estimate for my area is given by the number of indices, the proportion of the darts that fell in the disk, divided by the total number of darts I threw at my dart board, which had an area of 4 because it was a square of side length 2. That is it. And then I return a tuple. I'm not using the tuple notation, but this returns a tuple. I return all the darts I threw, the indices of those darts that fell in A, the indices that did not fall in A, and an estimate of the area. Let us run that code cell. Now I have a plot random disk darts that I interact with a widget. I suggest for you to create a variant of this function that uses a while loop to generate n samples within A and also returns the total m samples needed to generate the n samples. So that's something to read and think about, and I highly suggest you do it. But let's just look at this example. So here I'm returning everything from the random disk darts function, and then everything else is plotting. I plot a circle to indicate the set A, and then I plot the darts that landed in A as black X's. And then I use blue circles to denote the darts that did not fall in A. And then I show the estimate of the area. So let us look at this, and I allow you to vary, and this is a manual interaction because there's random sampling involved. You can vary the number of darts you throw that you simulate throwing. So let's imagine we threw 100 darts. So you see the black darts fell in that disk and the blue darts did not. This looks very much like this type of plot that we see on the Monte Carlo integration webpage in Wikipedia. So the area of the disk, which is, we know from geometry, pi times r squared, where r is the radius, gives us the area of a disk. Well, the area of this disk has a radius of 1. It's just pi, which is about 3.14. So 100 darts actually gave us about an area that is close to what the area of a rectangle, what the area is. Let's actually run this again. About 3 right here. If we do it again, 3.2. We do it in 3.16. These are not too bad. Let's look at using 1900. About 3.15, and look at how more densely we filled up our dartboard with all of these darts. 3.15 is a pretty reasonable approximation to 3.14. If I run this again, 3.17, no surprise, we have a reduced variance in our results because we're using more samples. So here's my activity for you. Integrate over the dartboard. Based on that random disk darts function, create a new function called my_mc_disk. So these are going to create Monte Carlo approximations to integrating a function on that disk. You are going to estimate the integral of a function f over the unit disk. This function should have as input parameters f, n, and f, f and n, where f is the function to be integrated, and it should output an estimate of the integral of f over the disk using Monte Carlo approximation. You can use the random disk darts function, which was shown here. Here's my random disk darts. And there are 2 lines of code that are needed. One is to compute the average value of the function evaluated on the darts that fell inside of A. And the other one is then to approximate it. You just have to take these 2 lines of code and add them to this function. Copy and paste that function into here. Redefine the function name as myMCDisk. And then add these 2 lines of code. And that's you creating that function. And I want you to test that function for some different lambda functions of your choosing. I want you to create a plot MCDisk, which is based on the plot random disk darts function, and follow the instructions I give you here. I'm not going to read all of them to you right now. And I want you to demonstrate the plot random disk darts function and how it works on some lambda functions of your choosing. And so again, make sure you follow these instructions because I'm going to be looking that it does does what it should. And then I have a recommended but not required part of this activity, so I won't read that to you here, but you should read it carefully. And I do recommend you do it. And then finally, a summary that you have to provide at the end as usual. And make sure to write complete sentences for your summary points and code examples that are well aligned to the summary points that you're making. So that is it. Thanks for listening. And if you have any questions, of course, you can post on Canvas. And I will see you in a future video involving the homework assignment for this 4th computational module.